A study was done for a vitamin supplement that claims to shorten the length of the common cold. The data the scientists collected from 10 patients in an early study is shown in the table below. So you can see there are several things that we're asked to do in parts A, B, C, and D. I'm going to begin by, I want to look at this data in another form. A table is nice, but I'd like to look at it as a scatter plot. And definitely one of the ways we've done that in class is with our TI-84s. And that's a great tool. Unfortunately, when you go home, a lot of you don't have access to it. And I'll be honest, it's a dated tool. This is something that, honestly, it's related to technology your parents would have used in the classroom. I think a much more powerful and intuitive tool is Geogebra. This is a free download at geogebra.org, and it runs pretty much on any device you can think of. And we're going to look at this data using Geogebra. So when Geogebra starts, it typically starts with the algebra and the graphics view. And there's a lot of goodies here. This computer algebraic system is amazing. It's a very powerful tool. What we're going to do, however, is we're going to activate the spreadsheet because we want to look at this data. So I've activated the spreadsheet, and we only need the first two columns, so I'll slide this over a little bit. So you can see I can see column A and column B. In column A, I'm going to enter the number of months that a participant in the study was taking the supplement. And in column B, we're going to enter the number of days that their reported cold lasted. So we'll start with just entering this first row. It's a row in the problem there, but we're going to enter as a column. So we've got a 0.5, and we've got a 2.5, a 1, a 2, another 0.5, a month, 2 months, 1 month, 1.5 months, and then 2.5 months. So you can see the least amount of time that someone had reported taking the supplements was a half of a month, about 14 days, and the longest was 2.5 months. Okay, so now let's record the number of days the cold lasted with the corresponding participant. So the one who had the number of months taking the supplements that was a half a month, their cold lasts for 4.5 days. We've got a 1.6 days, a 3, a 1.8, 5, 4.2, 2.4, 3.6, 3.3, and finally 1.4. So it's a good idea once you're done, typing these values in, either in Geogebra on your calculator, to kind of double check and make sure you entered things correctly. In fact, I'm going to pause this video right now and double check myself. Okay, so I have verified all 10 values and they were entered correctly. The next thing we're going to do is we're going to create a list of points based on this data. So to do that, I'm going to click in the first cell in A1, and I'm just going to hold my mouse down and drag down and over until my mouse ends up at cell B10. Then I'm going to release the mouse, and then I'm going to come up here, and in this region I'm going to right click. I'm going to click with my right mouse button, and I'm going to go down to create. And unfortunately, you can't see what it says because it's off screen. So let me see if I can trick the system into create. Nope. It's off screen. But what you want to do is click create and then go, there it is. Come over to list of points. So again, right click, go to create, and then select list of points. And what it does is it creates a list of points called list 1. And furthermore, Geogebra went ahead and graphed all those points. Now I know the minimum and the maximum for my range, my domain rather, and I know the minimum and maximum for my for the range. So it's a good idea to come in if you select the when you're in the graphics view, right? These icons will change if you're in the algebra view or the graphics view. This is what they look like. But when you go to the data view over here, they change. So there's different sets of tools. I'm going to click in the graphics view, and with this tool selected, I can click and drag this data set around. And notice that if I bring my cursor and put it right over the x-axis, I get this arrow that moves left and right. And if I click and hold, I can drag my x-axis off. In fact, I could drag that further out. And I could do the same thing with my y-axis. I can take this, click, and stretch it up. So I'm seeing the data a little bit better. It's just slightly better spaced, and it's using up the region more. The next thing I want to do is, well, I could probably answer A at this point. It says describe the association. Well, the association I'm seeing is it appears that the longer one has been taking the supplement, it looks like the duration of the cold decreases. So you can see these people have been taking the supplement the longest, about 2.5 months, and they had the shortest reported cold length. Now, we're not saying that this supplement regime is what caused it. It could be other factors. It could be maybe these people that are just more reliable about taking the supplement take better care of themselves. But we are seeing that there's an association here, right? As one variable increased, the amount of time that they've been taking the supplement, the length of the cold decreased. The next thing we're going to do is we're going to model this data by creating a line of best fit. So down at my input task bar, I'm going to type the following. It's FIT, fit, and then LINE. So fit line, and then I'm going to press enter. So you can see you don't need to type it with capital F and L. It'll pop up and you can just press enter. But if you're going to type it completely, do capital FIT, capital LINE. And right now, list of points is selected here. It's the argument that I need to give it. What's the list of point that you want me to fit a line to, is what the computer is saying. And the line that I want to fit it to, the data is stored in list 1. So I'm just going to type list 1, LIST 1, and then I press enter. So this is the least squared regression line that best fits this data. And if I wanted to, I can drag this equation out and put it on display here. So the equation is there. And what's essentially happening is as x increases by 1 unit, you can see the y values are decreasing by about 1.5. So for every month that a person is taking the supplement, it looks like the duration of their cold decreases by about 1.5 days, 1.5 days. So let's read this here. It says, model the data with a line of best fit done. According to your model, how many days do you expect the cold to last for a patient taking the supplement for 1.5 months? Well, here's 1 month and here's 2 months. And if I wanted to, I could put a line right here to kind of show that. In fact, let me do this. I'm going to say I want x equal to 1.5. So this line, and in fact, I'll make this line red. I think you can pick color, and I'll make the line red. So what I'm saying, what we see on this line here is that this is someone who's taken the supplement for 1.5 months. And it looks like the model is predicting, if you look real closely, it's going through this point right here. The model is predicting that their cold would last for about 3 days. In fact, I could go ahead and grab the point tool, and I could create a point right at the intersection of 1.5 months and my model, and it's right there. So the model is reporting at point K that if someone's taken the supplement for 1.5 days, the cold should last about 3 days. So that would be my answer for B. For C, it says calculate the residual for 1.5 months. Interpret the residual in context of this problem. So the residual for 1.5 months, if you look at it, I've got this one data point right here, and you can see what's happening. This is the value that was recorded in my data table. In fact, you can see it right here. At 1.5 months, this person reported that their cold lasted for 3.3 days, which is 3 days and about 3 hours, right? A third of a day is roughly, well, no, a third of a day is 8 hours. So this is 3 days and 8 hours is how long their cold lasted. But this is what the model is saying. Remember, this is our model that we built, our linear model based on all the data points. And you can see that there's a residual here. There's a difference between what the model says and what the observed data point says. Now that distance between those is the residual. In fact, I could grab this tool and I could click in here. I'm going to calculate the distance between those. So I'm just going to click I and then K. And what it says is the distance between I and K is 0.3. Well, I could have figured that out, right? What we're saying here is that this is a residual of 3. Remember, residuals are always the observed value minus what the model says. So observed minus the model. Residuals are positive if they're above your model, and residuals are negative if they're below your model. So calculate the residual for 1.5 months. Interpret the residual in context of this problem. Well, in the context of this problem, what we're saying, and I'm zooming out here, is that someone who took the supplement for 1.5 months, the model predicted that their cold would last for 3 days. And you can see that the person who actually did take it for 1.5 months, their cold lasted for 3.3 days. And then finally it says interpret the Y-intercept in the context of this problem. So if I zoom out a little bit more, we can see the Y-intercept. We grab this tool and grab this over. You can see here's our Y-intercept. And the Y-intercept is basically saying, hey, if you've taken the supplement not at all, right? You've taken the supplement for 0 days. About how long would your cold last on average? So without this treatment, how long would you expect the cold to go without this supplement regimen? And I can get that by grabbing a point and constructing a point where my y-axis and my model meet, and that point is right there. And you can see it's at 5.37. which was reflected in the equation of my line of best fit, right? 5.37. And in context of this problem, what we're saying is if you don't take the supplements at all, the model's reporting that your cold would last for about 5.37 days. So more than 5 days, 8 hours. Anyways, I can't recommend this enough. It's a great tool. I could talk a lot about a lot of the features, and I will over time talk more and more about Geogebra, but it's a really good way to do homework. And you can basically grab this if you were to hit File, Export, Graphics View to Clipboard. You could copy this and then paste it into Word or some other program and print up your report and include it in your homework. I love to see stuff like this, and definitely you will never be docked points for doing, I think, the modern intelligent thing, using real data analysis tools to look at the situation. And Geogebra is certainly, there's much more powerful packages than Geogebra, but as in terms of the cost, you can't buy anything better than Geogebra because it's free. A line with a slope of -2/3 passes through the point 1216. What is the equation of that line? So let's take a look at a sketch of the situation, kind of a crude sketch, right? So I'm over here at x is about -12, and y is up a little higher than that, right? Y is at about 16. So here is about 16. So here's a starting point. The one point they gave us, -12 for x and 16 for y. And I know that if I go down 2 units, I will go over 1, 2, 3 units, and this would be another point. Down 2 units over 1, 2, 3 units, and that's another point. So somewhere in here there's a line, and unfortunately this is just a very crude sketch, but I need to figure out basically what's this value right here that we call the y-intercept. In order to come up with the equation of this line, we need 2 things. One of the things that we would need is the slope, which we're in great shape because we have. And the other piece of information we'd like to have that would make it easy to write the equation of this line is what's the y-intercept? What's this location? So to do that, there's one technique that perhaps you could consider. We look at the general form, or the slope-intercept form of the equation, y equals mx plus b. And what we're going to do is basically plug in the information that we have into this equation. One of the things we have is our x value from the point that we were given. We also have a y value from the point that we were given. And we also have this slope, I'll circle in red right here. This is our slope. And by the way, the slope, the variable that we use to represent that is m right below. So if I plug in each of those values in the correct places, I'm going to start with y, which is 16. I'm going to write right below the y here, 16, right, is equal to, and let's go ahead and grab our slope is negative 2/3. That's what our slope is. And then we're going to multiply that slope by the value negative 12, which is what x is, negative 12. And then when we're done with that, we're going to add b. Well, if you look at this thing that we've just written down, I have four values, right? I've got the 16, the negative 2/3, the 12, and then the only variable that we have is b. Well, this is exactly what we wanted to find. So in order to figure out b, I'm just going to solve this equation, and it'll tell me exactly what b has to be. So let's start by this business right here. I've got a negative 2/3 times a negative 12. Well, I know that when I multiply those two values, it's going to end up being positive. And if you look at this, I could look at, for example, 2 times 12 over 3 times 1. So if I'm looking at this is 2 times 12 over 3. I could simplify this first. 12 divided by 3 is 4. I have a common factor of 4 there. So this ends up being just the same thing as 4 times the number 2, right? 4 times 2. So this is positive 8. So this equation becomes 16 is equal to 8 plus b. Simple now, right? Subtract 8 from both sides. 8 is what b is. So I was wondering what that is right here. I know it is. Now this is where y is equal to the number 8. That's my y-intercept, right? Well, now that I have all of those pieces, I can go ahead and write the equation of the line. The equation of this line is y equals, then we plug in our slope, negative 2/3, and then times x, and then plus 8. So if I look at this equation, I know that when I plug in this one known point, it definitely will work. Also, if I plug in 0 for x, I'm going to get the y-intercept of 8. So that's the equation of this line. For each area model, fill in the missing parts. Write an expression showing that the area as a sum equals the area as a product. Okay. Well, let's take a look at this. Interesting. I think the one thing that I'm looking at, first of all, is definitely, I'm going to focus right here. If I multiply something and I get xy, and one of the things I multiply is x, that means the other thing has to be a y. So when I multiply x times y, I get xy. The other thing is if this is a positive 3, right, and I multiply it by this y, 3 times y is 3y. And then the last thing that I have is, well, if this value happens to be y squared, and I get that by multiplying by a y, that means that this value here has to be a y. So if I look at it, I've got two dimensions for this rectangle, right? One of the dimensions is y. The other one is x plus 3 plus y. So if I was going to write this as the area is the sum of the sum here is x plus y. I'm sorry, I didn't even write that down. Let me write it again and say the right thing this time. It's xy plus a 3y and then plus a y squared. Now if I compare that on the other side, what do I have? I have y times the quantity of x plus 3 plus y. Now again, it's not terribly intuitive, as we're starting out, why this is happening or what exactly is going on. But just to kind of bring this home, one of my dimensions is y, and you can see that's reflected right here. I'm multiplying y times my other dimension, which is x plus 3 plus y. And right here you can see the x plus 3 plus y. Now when I multiplication, those parts, what do I end up getting? I end up getting x, y in the first case. And this is basically the distributive property, right? So I've got the x, y, check. You could say y, x too, it's the same. And then I've got a 3y, or y times 3, check. And then the last one, y times y, is y squared. You see that? That's check. Okay, so now that we've looked at one of these, I think the second one might be a little bit simpler. I hope so anyways. As I take a look at this, I would say, I would say just my guess of it is that there has to be an x here, because if I multiply an x times, well, there's going to be an x there. And in fact, now that I know that that has to be an x, I'm pretty sure this has to be an 8, and this has to be an x also. So if you take a look at it, when I multiply y or x times x, right? X times x, you can see I get an x squared. And then in green, when I multiply this x times this 8, I get 8x. The other thing I have here is I'm going to multiply a 3 times an 8. And when I multiply 3 times 8, this box has to be a 24. And the final one is I'm going to multiply a 3 times an x, and this would have to be 3x. So if I look at these pieces, right, on the one hand, I've got an x plus 3, and I'm multiplying that by an x plus 8. So that's the dimensions of it, right? Those are, here's one of the dimensions is x plus 8. You can see I've got that there. And my other dimension that I have is a x plus 3. And you can see that's reflected right here. So the question is, once I multiply those, what exactly do I get? Well, you know, I'm looking at the model right now because the model's here and it tells me exactly what I get, right? In the one hand, I've got, and I don't want that to be blue, I've got an x squared, and then I've got a plus 8x, and then I've got plus 3x, and then finally I have plus 24. And typically when we look at this and we write them down and we realize, hey, two of our terms are like terms, they have the exact same variables with the same powers on those, we can combine like terms, right? So probably my final answer would be x squared plus 8, 9, 10, 11 x's, and then plus 24. Okay, so for 28, we have two different functions. One of them f of x, which is basically the function that takes an x, and to evaluate it, it's 3 minus the absolute value of the x you give it. And the other one is it takes the x, raises 3 to that power, and then adds 5. And it's asking for us to evaluate a few of these. We're just going to do actually a couple of these. I'll say we'll go ahead and do f. I guess we'll do D, and we'll do A. So we'll just do those three only. So let's do A first. So f of -5, right, is equal to 3 minus the absolute value of -5. When I look at this, the absolute value of -5 is 5. So this becomes 3 minus, and again, the absolute value of -5 is 5, so it becomes 3 minus 5, which is -2, and that's the answer. D, let's see, A, B, C, D. Let's look at D. This is also f. This is f of 2, and that's going to equal 3 minus the absolute value of 2. Well, the absolute value of 2 is 2. So this is 3 minus the 2. 3 minus 2 is equal to 1. You know, a common error that you can see kind of sometimes is students might look at this and say, hey, there's an absolute value here. All the negatives go away. No, don't do that. Be very careful and be intentional, right? The absolute value, we're taking the absolute value of the expression that's inside of here, right? The -5, what's the absolute value of that? That's 5. What's the absolute value of 2? It's 2. But you can see that this negative symbol is in all of those problems, and it's not going away. It's 3 minus something, and the absolute value of x is that something. I circled, oh, the last one I did was G. That's good. So let's look at G. So this says G of 0, and G is 3 to the 0 power, because that's what our current value of x is, and then plus 5. This 3 to the 0 power is equal to 1. We've looked at that inductively in class. If you're not convinced of it, play with that and get to where you're really comfortable with recognizing when I have a value and I raise it to the 0 power, it equals 1, and then 1 plus 5. So G of 0 is the number 6. Solve the equations below by first rewriting each equation as a simpler equivalent equation. Check your solutions, it says. Well, as I look at this, for the first one, my first thought is I don't like fractions in problems I'm dealing with. So believe it or not, I'm going to choose to multiply both sides of this by the number 70. And in fact, I'll write it as 70 over 1. But I'm going to multiply every single term on both sides of that equation by 70 over 1. And remember, terms are those things that are separated by the plus minus symbol. So if I do this, this was 2/7 times x. And I think I'll just go ahead and put my new factor of 70 over 1 in front of that. So you can see that I had a 2/7 x, and that now has a 70 over 1 factor that's been tacked onto it. Then I've got plus 2, and I might write it as 2 over 1. But then don't forget, this also needs the 70 over 1 factor as well. And then finally, on the other side, we've got 3/10. But let's not forget, this is going to get a 70 over 1 factor as well. Now, the reason why I do that is I know multiplying both sides of that by 70 will completely obliterate all the fractions throughout this problem. In the first case, 70 over 1 times 2/7 ends up being 10 times 2, or 20x. So all of a sudden, I don't have a fraction there. That's now 20x. The next thing I have is 2 times 70 is 140. And on the other side, that's going to equal 70 divided by 10 is 7 times 3 is 21. So the beauty of this is, right, because if you have equal things and you multiply by equal things, in this case we're multiplying by 70 over 1, both sides, all terms, you get equal things. So because this statement was true, right, this statement is also true. And it's true because of the multiplication property of equality. Equal things times equal things produces equal things. So I haven't changed the truth value of this equation. If the first equal symbol is true, this one is true also. Now let's go ahead and subtract 140 from both sides. So I've got 20x, and I'm going to now take the number 21 and subtract 41 from that. And I apologize, but yes, I'm literally firing up a calculator and going 21 minus 140. And I know it's negative, and it's actually 20x is equal to 119 negative. Now I'm going to divide 119 by 20. Now that's not pretty, but I end up getting that x is equal to negative 119 over the number 20. And if you're really fond of this thing, you can take that thing and you can kick it into a, oops. It's equivalent to negative 5 and 19/20. And either answer is fine. My preference is probably this first one, just because it's easier to check it. I really like to grab a calculator and just throw that into it. In fact, I'm going to do that right now. I'm going to take 2/7, so that's just 2 divided by 7. And I'm going to multiply that by negative 119 divided by 20. Once I press equals there, I'm going to hit plus the number 2, and I get exactly 3/10. That's amazing. So basically, by plugging this into both sides, and actually there was just the one spot where x was, right? When I plugged it in there, it turns out that this whole left-hand side becomes exactly 3/10, which is what I need. And it's the evidence that that is indeed the value of x that makes this equation true. Now, the next problem, it turns out if I multiply both sides by 50, it would be a perfect way to get rid of all the fractions. So let me see, I'm going to use green here, and I'm going to multiply both sides by 50 over 1. Now, they're all fractions, so what I'm essentially going to do is put a factor of 50 in each one of those numerators. So I'm going to have a 9 times 50 over 50 plus 6x times 50 over 50. And that's going to equal 3 times 50 over 10. And I just lied here. This isn't, you'll never see it, but that is actually 9 times 50 over 50 plus 6x times 50 over 25, and that equals 3 times 50 over 10. So basically, look very closely and verify that Mr. Roberts did indeed add a new factor of 50 to all terms on both sides. You might be saying to yourself, why are we adding a factor of 50 to both terms on all sides? Isn't that kind of like doubling up the 50s on one side? And I understand why you're saying that, but let me just kind of demonstrate why that's not the case. Just consider the following statement, right? 2 plus 3 equals 5. I think all of you logically agree in the truth of that. You might be tempted to just add the 2 and 3 and you get 5 as 5, right? I want to suspend that for a minute because I want you to show you why it is I need to multiply all terms by 2. So let's say that I'm going to multiply both sides of this by the value 2. When I do that, I have to hit all terms on both sides with a factor of 2. So that becomes, on the left-hand side, a 2 times 2, and then plus a 3 times 2. And then over here, that equals a 5 times 2. Now, arithmetically, or using arithmetic, you can verify that on the right-hand side, it's clearly 10. And on the left-hand side, it's 4 plus 6, which is also 10. So that's why it's really important when we multiply both sides by this value 2, right? We have to hit every single term on both sides by that factor, that new factor of 2 that we're multiplying by. Now this equation's become, back to our original problem, become vastly simpler, right? Because now it's simply 9 plus, let's see, 50 divided by 25 is 2, so that would be 12x. 50 divided by 10 is 5. 5 times 3 is 15. I like it a lot. 15 minus 9 is the number 6. So I've got that 12x is 6, and x is equal to 6 divided by 12, which is just the number 1/2. So we've got that x is 1/2. And again, you could throw that in, if you do 9 divided by 50 plus 6 times 0.5, divided by 25 equals, I get 3/10 again. At Jacques Bistro, they serve 2 sizes of espresso, small, denoted by S, and large, denoted by L. And I gotta say, before we move on, I think this problem was poorly designed. I think the intent of the author was to say that the cost of a small espresso is S dollars, and the cost of a large espresso is, what is it? Let's see, L dollars. So I think if S and L are the cost, S is the cost of one small and L is the cost of one large, this problem makes a lot more sense. Outside of that, I'm kind of scratching my head like, It says in a given day, they made X of the small. So right here, they're telling me they've made X of the small drinks. And again, the small drinks cost S dollars each. And they made Y of the large drinks. And again, the Y drinks cost L dollars each. So what do each of the following expressions mean in context of this problem? So S plus L would be, I guess this would be that's pretty straightforward. It would be the cost of one small and one large. It's like one to get you started in the morning, and then one for later on as a booster shot. Let's see, what would be X plus L? Well, if X is the number of smalls that they made and Y is the number of large they made, this would be the total number of espressos sold, right? Some were small, some were large, but that's the total number of them that was sold. And then this right here, right? If I take and I multiply it that I sold X of the small ones, and I sold Y of the large one. Remember, Y was how many, and X was how many of their respective espressos. What this is it represents the total revenue that I made for selling, and this would actually be the gross, right? There's the total revenue that I made from the small and the large espresso. So this is the total dollar value that total value of the large and small espressos sold. So that's the money. So the value. So we've got the number of them, the value, and then we have the cost of one of each.